So welcome you all to our tutorial on polarization-based computer vision. My name is Jingwei Yi. I'm assistant professor at George Mason University. And our tutorial is a half-day tutorial, starts from 9 and ends at 12 p.m. at noon. And we have 4 speakers lined up for this tutorial. That's me and San-Juan Baek from Postdoc, Chuda Kadembi from UCLA, and George Chen from Vayu Robotics. Okay, so before starting the talks, let me give you some brief introduction about our motivation and your expectation from our tutorial. Okay, so what is polarization? Polarization is a concept in physics that describes a property of light. As you know, light is a form of an electromagnetic wave, okay? And polarization describes the oscillation of the electric field. So why we care about it in computer vision? Because polarization is very helpful for many computer vision tasks. For example, it helps to remove some unwanted visual effects like a reflection or a flare, or it helps to make some visual features more salient than color images, and is very commonly used in deficiency detection in industry. And as of now, polarization camera has been commercially available. So now we have new sensors with polarization filters that are aligned on top of the sensor, so we can do snapshot polarization imaging. Okay, so that makes polarization, the application of polarization, more and more popular nowadays, and that is the purpose for our tutorial. We want to introduce polarization to more people, and so you are aware of how to use it in your specific problems. So the goal of tutorial is to help you gain some basic understanding of polarization and know how to use it for different computer vision problems. So specifically, you can expect to learn about the physical background and representations of polarization, how to measure polarization with camera, the representation of material using polarization data, and also how to do 3D reconstruction, use polarization cues. Also how to combine polarization with deep learning method for different kinds of reasonings. And finally, we'll have talk about how to use photometric imaging for industry as well as for robotic perception tasks. So here's a brief schedule of a tutorial. Our tutorial is a half-day tutorial. And after my introduction, we will have the first talk by San-Juan Baek from Postdoc. He will talk about the introduction of polarization and photometric BRDF. And then I will give a talk on polarization-based 3D reconstruction, and then we will have a coffee break. And each of the talk will be 40 minutes, which also includes 5 minutes QA. So the actual talk time will be around 35 minutes or so. Okay. And then after the coffee break, Chuda will give a talk about deep learning and polarization. And the last talk will be from George Chen, which is on enhancing real-world robotic perception with photometric imaging. All right, so without further ado, let's welcome our first speaker, Professor San-Juan Baek, and he will talk about polarization, give an introduction of polarization and also polarimetric BRDF. Okay. So while we are switching the computer, let me give a brief introduction about San-Juan. San-Juan is an assistant professor at Postdoc in Korea. He works on problems at the intersection of computer graphics, computer vision, optics, imaging, and machine learning. And before joining Postdoc, he was a postdoc at Princeton, and he got his PhD in computer science from KAIST in Korea. Okay, let's have San-Juan get started.
Okay, thank you for the nice introduction. I'm Seung-Hwan.
You didn't turn on your video.
Oh, sorry. All right. All right, this should be good, right? Hello, everyone. I'm Seung-han, assistant professor at Postech. And today, I'd like to talk about the introduction to polarization and polarimetric BRDF. So this hopefully will warm you up to learn something about the polarization throughout. Oh, give me seconds so that the online attendees also can see my face. Okay. Okay. Let me begin. So before beginning my talk, let me introduce myself. So I'm Seung-han again, the leading computer graphics lab at Postech, and I've been working on computer graphics, computer vision, optics, imaging, and display. And of course, I have done some of the polarization works, just like the other organizers in this tutorial. And in this very first session of our the polarization tutorial, I'll talk about the backgrounds and applications of the tutorial briefly. And I'll spend some time on explaining the representation of polarization, especially mathematical representations. And also I'll describe the polarimetric BRDF, which is a concept similar to the BRDF, but its extension towards the polarization of light. And also I'll talk about briefly about the ellipsometry, which is an optical imaging technique for acquiring the polarimetric BRDFs. So as Jinwei explained in the very beginning, the light is waves, right? And we know that light is electromagnetic wave as the Maxwell described, and light consists of two perpendicularly oscillating waves. One is the electric field, the other is the magnetic field, right? And polarization is a wave property of light, and it describes the geometric oscillation pattern of light's electric field. So one way to explain polarization is to project this geometric oscillation pattern of electric field to a tangent plane perpendicular to the propagation direction of light. So once you project the trace of this electric vector, then it has some shapes, right? And that describes the polarization state of light. So depending on this oscillation pattern of electric field, we can say that the light is sometimes linearly polarized, as you can see on the most left side, or light could be circularly polarized, or light could be electrically polarized. So actually, in fact, there are infinite number of polarization states that you can describe. So first, let's have a look at the representative polarization states, the most popular one, linear polarization. Here, for this linearly polarized light, the electric field oscillates in a single plane. Okay, so that's why we also often call this as the plane polarized light. And here, in other words, the trace of this electric field is linear. Okay. This is the circular polarization. Here, the electric field, electric vector here rotates counterclockwise from the viewpoint of the observer. So as you can see on the right side, this the tip of these arrows rotates counterclockwise from the viewpoint of the observer, right? So here in this case, we call this one as right circularly polarized. Okay. So these kinds of circular polarization can be explained with the sum of two perpendicular the two linear polarization of light waves. Here, as you can see, this horizontal one and this vertical one. These two are the electric fields, and if you sum these two up, then we can draw this the electric vector rotating counterclockwise, right? So this can be made with the two plane waves of equal amplitude with 90-degree difference in phase. I mean, if you know about the phase and amplitude of waves, this is another way of interpreting the circular polarization. And the last one that I'm going to talk about is the elliptical polarization. So this may feel a bit not that clear to you, because in computer vision, we mostly deal with the linear polarization, but elliptical polarization is actually the most general state of the polarization in the real world. Here, we can explain the elliptical polarization with two in-plane plane waves, I mean, which are the linearly polarized plane waves that have different amplitudes, or plane waves with the different phases. So if you sum up two different plane waves with the different amplitudes, or if you sum up two different plane waves with different phases, right, then they're going to draw this elliptical polarization kind of thing. Okay. So this is the most general state of the polarization. So that's it for the three representative states of the polarization. And now let's see why we study polarization. So our human vision system is really good at sensing the wavelength-dependent light intensity in the visible spectrum from 400 nanometer to 700 nanometer. We can distinguish these light with different wavelengths as different color perceptions, right? However, the problem is our human vision system is not that sensitive to the polarization state of light. I mean, often in the literature in computer vision and computer graphics, we often say that human vision system is not sensitive to polarization. And that's mostly true, even though we actually, you can actually sense polarization a bit. Like there is a popular effect called the Heidinger brush. So which you can see the glimpse of the polarization effects with your naked eyes by looking at the sky under the sun at a specific angle, or if you look at the LCD screen at such a specific angle for like 5 seconds, something like that. So if you want to know more about your polarization sensitive vision, look for this Heidinger brush on Google, and you'll find the information. So in contrast to the human vision system, the vision system of various animals are known to have this polarization sensitivity. I mean, very famous, this mantis shrimp's eyes, or the bees, the octopus, and so on and so on. And their vision system are known to make use of polarization, probably for their living, even though, I mean, we don't know why they have the polarization sensitivity exactly, but I mean, we can guess that it would be helpful for them to see through some scattering media or detect some interesting polarization effects that may be helpful for their living or for some interesting for fun. Okay, and in animal vision, this polarization has been very extensively used, and unfortunately, not in the human vision system, but artificially we have exploited this polarization quite extensively. Okay, and in computer vision graphics and other communities, have been realizing this the value inside of the polarization information. So notable examples are the shape-from polarization, as probably many of you know, or diffuse specular separation, reflection removal for better photography, or seeing through scattering, the accurate detection and segmentation of polarization-dependent the signals. And today, I mean, today the follow-up, the organizers will probably provide some more detailed information of these applications. And I'll just, enumerate things here first. Okay, that was the basic introduction of polarization. Okay, what is the polarization, and what are the applications of the polarization, and so on and so on. So here, from now, I'm going to introduce the basic mathematical representation of polarization, which you may need to understand the following the content from the other organizers. First, back to the polarization, the concept is definition. Polarization, as I mentioned, is the geometric oscillation pattern of the light's electric field. And we can project these electric vectors, this oscillation pattern, to the tangent plane, right? To the propagation direction of light. So if you project this electric, the vector, then to the tangent plane, then you can get these kinds of like some shape. And this is called as polarization ellipse, okay? And polarization ellipse can be parameterized with two the factors. One is the orientation angle, the other is the ellipticity angle, okay? And by adjusting the values of this orientation angle and ellipticity angle within some bounds, then you can describe that this light is linearly polarized or circularly polarized or elliptically polarized. Okay, so this specifically orientation angle, this is often called as the angle of linear polarization or angle of polarization in computer vision community and also and other fields as well. And ellipticity angle, here for the linearly polarized light, this ellipticity angle is often 0. Okay, that makes this trace to be a linear line. If this ellipticity angle is 45 degrees, it becomes the circularly polarized light. Okay, and depending on the sign of this ellipticity angle, the circularly polarized light could be right-handed and then it could be left-handed. So that is the polarization ellipse. And now you know what the polarization ellipse is. And let me then dive into the mathematical tools for polarization. One is the Miller calculus, the other is the Jones calculus. And Miller calculus here, we have two concepts. The first one is Stokes vector, the other is the Miller matrix. For Jones calculus, we have Jones vector and Jones matrix. So for the Miller calculus, with the Miller calculus, what you can do is we can describe any light polarization state. So the light could be partially polarized. I mean, we can describe this polarization state of the partially polarized light perfectly with the Miller calculus, Stokes vectors, and so on and so on. And this is the main, the mathematical tool that we're going to use throughout this tutorial. And this is most probably the mathematical tool that you're going to use for using the polarization in computer vision. However, there is another important representation, which is the Jones calculus. So if you are dealing with some of the more like the wave nature of lights for interference, diffraction, holography, then Jones calculus is something that you would need, but it can only describe the fully polarized light. And today I'm going to only focus on the Miller calculus. So Stokes vector first. Stokes vector is a description of polarization state of light as a 4x1 vector S here. Okay, so usually we describe the intensity of light with a single value, right? It could be a radiance. But here, Stokes vector, we have 4 values: S0, S1, S2, and S3. And these 4 values represent the total intensity of light and intensity difference of 0-degree linear intensity and 90-degree linear intensity. And the third element describes the intensity difference of 45-degree linear intensity and minus 45-degree linear intensity. The last one, the difference between the right hand circular intensity and left hand circular intensity. So with these 4 values, now we can describe any polarization state of light, okay? And for example, if the light is unpolarized, so I actually didn't describe what the unpolarized means, but it is virtually same as the randomly polarized. If you project the trace of electric fields, then I mean, it is distributed uniformly random in this the tangent plane, then we call it as randomly polarized or unpolarized. And in many cases, like if you put the laser light into the diffuser, optical diffuser, then the output is usually the unpolarized, something like that. So unpolarized light Stokes vector can be represented as 1, 0, 0, 0, because the all polarization states are equally distributed. The linearly polarized light horizontal can be described as 1, 1, 0, 0, and so on and so on. Okay, so these are the basic representations of the polarization states with Stokes vectors. The next concept that you may need to know is the degree of polarization, in short DOP. And here denoted as rho. This DOP describes the portion of light which is polarized. So very simple. We get the square root of S1 to S3 and divide it with the S0. So how much of light is polarized given this entire energy? So this is the degree of polarization. So now you know what the polarization ellipse is, what are the Stokes vector elements, and you know what the degree of polarization is. Then we can define these Stokes vector elements again with these three parameters: the orientation angle, elasticity angle, and degree of polarization. Here, S1 can be defined as multiplication of S0, the total intensity of light, right? And rho, which is the degree of polarization. And then we have some interesting cosine terms. The cosine 2 psi, here psi is the orientation angle, and cosine 2 chi. Here chi is the ellipticity angle. And we can define the S2 and S3 similarly. And these the definition of these Stokes vectors, Stokes vector elements is actually very useful because we can naturally derive this validity of the Stokes vector. So for instance, I mean, the Stokes vector is the four-dimensional vector, right? S0 to S3. That doesn't mean that any four-dimensional vector is a Stokes vector, right? There is some specific constraint that a 4x1 vector to be a Stokes vector. And that constraint is actually written like this. The S0 should be the upper bound of the polarized light intensity, right? Root square of the S1 square plus S2 square plus S3 square. And that is because the degree of polarization is bounded by the 0 to 1. Okay, and another thing worth to mention is that the Stokes vector is defined with respect to a particular coordinate. Okay, why is it the case? If you recall my previous explanation of polarization, what we did is, okay, we have some trace of electric fields oscillating in space, and we projected that onto a tangent plane, right? But here, the tangent plane doesn't have axes. It doesn't have X and Y axes, so we should give that. So you can draw X and Y wherever you want, as long as XY forms a like orthonormal basis with the propagation direction. So there are infinite choices of n, x, and y that you can choose here, right? And what that means is if you then now record this the polarization ellipsis definition, and it's the angle, the orientation angle, and the ellipticity angle. These angles are defined with respect to those chosen x and y axes. So what that means again is that the even though the polarization state of light is same, its description with the Stokes vectors, there could be infinite number of possibilities depending on what to choose for the x and y axes, right? So that's why whenever you describe that the light polarization has the Stokes vector of A, then you should mention that what is actually the coordinate of that corresponding Stokes vector. Okay, next, now you know what the Stokes vector is. Then what is the Miller matrix? Miller matrix is a 4x4 the matrix that describes the change of polarization state by being multiplied to a Stokes vector. So if you have a Stokes vector here denoted as S before, and you multiply a Miller 4x4 Miller matrix to that Stokes vector, then there's another output, which is a Stokes vector, 4x1 Stokes vector, here denoted as a S after, right? So what you can do with this Miller matrix is that, for instance, I mean, if you buy some optical elements from the Thor Labs or any others, the optical vendors, then this polarization modulation of optical elements has its associated the Miller matrix. So they have calibrated their optical elements. They know what these values are. And then what you can do is you can calculate what would be the Stokes vectors after the shine the laser through these optical elements, something like that. And notable examples of these Miller matrices for basic examples: linear polarization, horizontal, the vertical, quarter wave plates, and so on and so on. These the corresponding Miller matrices are shown like this, but you can find more general formulas of these the optical elements on the internet for sure, if you want. Here, also one thing to highlight is that, okay, Miller matrix is multiplied to a Stokes vector, and Stokes vector should be defined with respect to a certain coordinate, right? And the output of the Miller matrix is another Stokes vector, and that output should be also defined with respect to a certain coordinate. What that means is, when you say something about the Miller matrix, when you explain the these optical elements or these materials Miller matrix is something, then you should also provide the corresponding input and output Stokes vectors coordinates as well, right? So that's that. Okay, that was the representation of polarization and depolarization change with the Miller calculus. Now you know what the Stokes vectors and what the Miller matrices are. Now let's visit this concept of bidirectional reflectance distribution function in short BRDF. So in computer graphics, computer vision, and even in optics, we have extensively utilized and relied on this concept of BRDF, right? And BRDF governs how much of light will be reflected from an arbitrarily incident direction to an arbitrarily the outgoing direction, right? So basically, it determines the visual appearance in terms of the intensity, right? And fortunately, there are great models of the BRDF. I mean, Lambertian BRDF model, Blim-Fong, Cook-Torrance, and I mean, there are neural models and so on and so on. There are lots of great analytical or neural models available. And with this, what you can do is, I mean, we can render beautiful images, photorealistic images. We can actually estimate the photorealistic material parameters by inverse rendering, blah, 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 right? So this is one of the main ingredients that enable the computer graphics, computer vision researches. Then what is the polarimetric BRDF, in short, PBRDF? So it is a simple extension to the BRDF. So BRDF describes how light intensity changes, right, after reflection. And here PBRDF describes the change of polarization, okay? How the polarization state of light changes given the arbitrarily incident direction and also arbitrarily outgoing direction. So that is definition of the PBRDF, and often we use the Miller calculus for describing the polarization state of light. So this PBRDF, we mostly use the Miller calculus as well as is the formulation. So then what is the relation between the BRDF and PBRDF? Actually, PBRDF is just a superset of BRDF. So why? If you recall the the definition of the BRDF, if you recall the definition of the Stokes vector and Miller matrix, the very first element of the Stokes vector is the total intensity, right? It is just same as the radiance, something like that. And then the Miller matrix is the first, the Miller matrix is the very first element. So describes just the BRDF if it is applied to the reflection, right? So here, BRDF is a scalar valued function, and PBRDF returns the Miller matrix. And the very first element of the PBRDF, that is actually same as the BRDF. That is that. Then what about the analytical models of the PBRDFs? Unfortunately, we have some, and I contributed the one model to this existing PBRDF models. However, I would say it is very far from being perfect. I mean, the existing, compared to existing BRDF models capability of describing this real world visual appearance, this PBRDF model is very premature. But still, we have some models, beginning from the 2000, 2009, 2018, 2020, 2023, and even like probably you know there's the very famous rendering engine Mitsuba 3, and in Mitsuba 3 we have this my previous 2018 polarimetric the PBRDF model that you can use to render the polarimetric images shown on the right. The rendering engine itself, this integrated into the path tracing formulation, is almost done. I mean, it's very well engineered, and we can render high quality polarimetric images in the form of the Stokes vectors, actually. However, this model itself is not perfect. But let me today briefly explain the one of these PBRDF models, which is actually my model. And first, just like the existing the BRDF models, we divide the reflection into two. The first one is the specular component. The other is the diffuse component. Okay. And what is the specular component? Based on the microfacet theory, which is, I mean, which could be true in the real life and may not be, maybe violated in some cases, but anyway, based on the microfacet theory, if we have an instant light coming into this direction, for a small part or microfacet level of this surface, we have lots of small facets distributed into the different places. And the reflection from these microfacets, right, direct reflection from this microfacet is known to be the main factor for the specular reflection. And so among the many different kinds of facets with different orientations, right? And for a particular for the particular outgoing direction, this specular reflection is believed to be, or model to be, originated from the direct reflection from the microfacets that has the microfacet surface normal aligned with the halfway vector. What is the halfway vector? Halfway vector is the middle way between the incident and then outgoing vectors, right? So then, given this, the previous assumptions of the microfacet models, we can model the PBRDF of specular reflection with PS equal to K. Here, K is the scalar coefficient model with the normal distribution for NDF and geometric shading. All of these are same as the conventional the microfacet models in physically based rendering and the material kind of thing. And in addition to that, we have additional 3 different terms: the coordinate convergent Miller matrices and the Fresnel reflection Miller matrix. These are the special treatments that we made for modeling this the specular PBRDF. But I mean, actually, if you look into in details, it's nothing special. We applied the old Fresnel theory of how the polarization state of light changes after the reflection on a specular surface. Next is the diffuse PBRDF. So what is the diffuse, what is the definition of the diffuse component? There could be many contributing factors, but here in this model, what we focused is when the light comes in, then some of the light would be would penetrate into this interface and then stays inside of this object and comes out, right? And that's why we see the some of the colorful the appearance of many objects, right? Because it interacts with the intermolecular the things inside of some materials. And here we also apply the same the mechanism of applying the coordinate conversion and then the depolarization Miller matrix and Fresnel transmission Miller matrices. Here I will not describe the details of this, but basically we just try to model how the polarization state changes after entering this interface and interacting with the inside of the material and so on and so on. And then if you sum these the PBRDF of the diffuse and specular, then there will be the total PBRDF, just like the conventional BRDF models. And there are, the many other variants of the PBRDF models, but these days the basic mechanism is okay. We try to decompose the entire light transport into, for example, diffuse, specular, or even the scattering, something like that, and then they try to model each polarization change individually and sum them up. There will be the PBRDF model. All right, and then the last part of my session would be the data set for PBRDF and ellipsometry. Okay, now we know what the PBRDF is, and we studied the analytical model of the PBRDF. But the question is, okay, it was a little bit weird. When I first got into this field, because okay, I made the analytical model of the PBRDF. Then it should model the PBRDF of real-world the objects, right? Real-world materials. Then the question is, okay, then how could we evaluate it, right? And the problem was there was no data set at all, right? And how the polarization state changes after reflection on the real-world objects, right? I made a model, but in order to evaluate it, we needed this some data set for doing that. And actually, in VRDF, the community, we have great resources of the large-scale VRDF data sets. The Wenzel made one, and also a long time ago, the Maciusic also made a really great data set of MAR VRDFs, and that has been the main the source for the developments of this BRDF related researches. But for polarimetric BRDF, PBRDF, we didn't have that kinds of data set, right? There were some papers that proposes some of the data sets that they captured. However, unfortunately, they had the limited directional coverage. They only measured the BRDF on a single plane, or they cannot measure the full Miller matrix of the PBRDF, and only a few materials, and there has been no public data set before. So what we did at that time is, okay, then we can apply the computer graphics methodology with the old optics stereoscopic ellipsometry for acquiring the first data set of the PBRDF. And this allows us to capture the PBRDF of the material quite at a high speed, and it took like 3 days per each material. And I'm not kidding, this is really fast acquisition actually compared to the previous the methodologies. With the previous methodologies, it took months for capturing the PBRDF of a single material. So the idea was, nothing special. In the optics community, what they have developed it, and they have extensively used these kinds of technology for various applications, not that much related with the computer vision, but still very useful for the science and engineering. They put the polarizer and retarder in front of the light source, and also the other the pair in front of the camera, and they capture a scene by rotating these retarders at different speed rates. Okay, then but after capturing the data with this, then we know the Miller matrices of these polarizer retarders already, as I showed before, right? And then we can make a formulation for solving an optimization to estimate the Miller matrix of this material that we are capturing. So that is the ellipsometry with rotating retarders. If you want to know more about the details of the ellipsometry with the rotating retarders, there are some references on the bottom. But with this ellipsometry technique, what we did is we captured the first PBRDF data set that exhibits this large directional coverage, complete polarization change on 25 real-world materials. So if you multiply 3 days to this, then it took almost like the 2 months, something like that, for capturing this. And we can use it for understanding what are the PBRDFs of the real-world materials, and also how could we utilize it for some applications that we still are still under investigation. And this is an example of the capture video for a Gauge sphere. Here, the 5 different rows represent the different the wavelengths of light, and here the columns they show the retarder angles, and we rotate the illumination, the arm from the opposite side to the front, something like that. So this is the capture data, and how to estimate then the PBRDF of this material is very simple. Back to the old least squares the solution for the optimization. Basically, for each turntable angle, we have this data of wavelengths and retarder. And then we fix the wavelengths, and we have this series of images with varying retarder angles. Then we focus on each of the pixel. Then we have the pixel intensity for each the turntable angle wavelengths. Then we have lots of the retarder angle observations. Then what we do is, okay, we know this observation F, and what we don't know are the is this PBRDF of this single pixel, and we know the Miller matrices of the analyzing optics, which is the combination of the polarizer and the retarder. We know the Miller matrix of the polarizing optics, also the combination of the linear polarizer and then the corner waveplate. Then we solve this optimization with a least square. Then what you get is the PBRDF of the reconstructed for this Gauge sphere element that looks like this. Then we tabulated this measured the PBRDF with respect to the wavelength lambda and also the Lewis-Cuisick parameterization angles. I mean, if you want to know about the Lewis-Cuisick parameterization, please refer to the PBR, the physically based rendering, the models. And overall, for a single material, we have the 1 GB size of this PBRDF table that you can use for rendering the PBRD, rendering the polarization, the characteristics of a virtual scene. Here we just assign this our scanned the PBRDF materials appearance to each portion of this the virtual scene. You can use it for rendering like this for realistic polarimetric the rendering with the real world materials, or also you can use it for discovering some hidden relation between the polarization with the material properties or geometric properties of the shape. So that was it for my part on the introduction of polarization and polarimetric BRDF. And before concluding my talk, I'd like to recommend you to check also out this great resource on polarization for graphics and vision. My friend Tizian, they made this really nice the tutorial or the kinds of blog posts on there, the Mitsiba, the description. So that could be also helpful for deeper understanding of polarization, especially for computer graphics. Okay, And that's it for my presentation. And I think I have 5 minutes, right,
Yeah, I think
for Q&A.
I think because right now we are a little bit running out of time, so probably
Okay.
we can only take maybe one question.
Okay.
Yeah.
Yeah. I'll be around also during the coffee break. So if you want to know more something, then you can ask questions.
Yeah, go ahead. We can take one question.
It's very difficult to actually say because in our data set, we capture things with the 50 nanometer difference, so which is quite a lot. And actually, if you there are some the analysis results that we presented in our paper. And if you capture, for example, the red, the billiard ball, and then the green billiard ball, right? And if you analyze this, the wavelength dependent PBRDFs, and they are substantially different. That's what we discovered. However, like if we, I mean, it highly depends on the materials that we are actually capturing, right? For some materials, I would say that likely we would see really interesting differences of the PBRDF for some materials, but for some others, probably similar, something like that. Yeah. Yeah, very difficult answer. Yeah.
You said you captured 50 nanometer difference in data.
Yeah.
So, like, is that a continuous laser that we use?
Oh no, I mean we actually use the spectral filter with the bandwidth of 10 nanometer. Yeah. Oh, I mean we didn't use tunable spectral filter. We used the hard coated, the optical glass type of the spectral filter. Exactly. And we rotated the filters one by one. Yeah, because the tunable spectral filter, this light efficiency is just too low. So yeah. Okay,
All right.
I think that's it.
All right, so let me map my computer to the projector. Some reason it's not showing up. Strange.
Oh no.
Oh, okay. Yeah. All right, the machine screen. All right, then in this talk, I'm going to talk about how to use polarization for 3D reconstruction. So I want to talk about polarization for material representation acquisition, and here I'm mostly focused on geometry estimation. And my name again is Jingwei Ye. I'm assistant professor in the Department of Computer Science in George Mason University. So the first method I want to share with you is that polarization is related to shape. And here I show you a visualization of the angle of linear polarization, which is the orientation of the polarization. Imagine that you project it on the plane, right? If it's a line, then it has a certain angle. If it's ellipse, then it's the orientation of that elliptical shape. And this map show you a visualization of that angle. And then if you look at the surface normal map, you can see they're actually correlated, and we can use an equation to represent their relationship. But if you are using the angle polarization for a normal estimation alone, then the normal angle that is estimated by this equation is up to a 180 degree ambiguity. So a lot of efforts has been put in how do you remove that ambiguity. And here in this talk, I will show you two methods that are developed in MATLAB on how to combine polarization with other physical-based cues for shape estimation. And here in this talk, the methods that I'm going to present here are mostly physics-based. And then in the next talk, Achuda will talk about learning-based method for invariance. Okay, so again, polarization is related to shape, and there's an underlying assumption, which is the light source, the light coming from the light source is unpolarized, which is true in many cases, right? Because light that is directly come from either a natural source or a man-made source like a sun or light bulb, they're all unpolarized, meaning that our polarization is along random directions. So if you have a light source like that, then your angle of polarization that you captured is only related to the shape of the surface itself, and that is related to the surface normal, which is helpful for shape estimation. But unfortunately, in the real world environment, this is not true, because we will have other light that is not unpolarized. We usually have some linearly polarized component in the light in the environment. So in order to do shape from polarization, people usually do the experiment in the dark room, which block out the light that is unwanted and only use a light source that is giving out unpolarized light. But if we want to do such estimation under a natural lighting environment, that poses challenges. And again, that is because we don't have control on the polarization state of the light in the environment. So for example, here I gave you some result that is actually captured under a uncontrolled natural environment. So think about an indoor setting, and then we take a picture of this sphere using polarization camera, and then we can have the directly measured angle of linear polarization, which is something like this. And you can see you get a lot of unwanted noise on this map, like this random colors, and this ruined the relationship, right? If you take a picture of the same sphere under a dark room, this is something you will have, which is a very good map of angle of polarization that is directly related to the geometry of this surface itself. So polarimetric Q is corrupted by the environment light. And again, why is that? This is because light from the environment has uncontrolled polarization state, and especially the linear polarization states corrupt this polarization Q that we want, okay? And why the light from the environment had this linear polarization is because reflection from any surfaces may introduce polarization to the light, although the light from the light source is unpolarized. So when you think of a way to overcome this challenge, which is by using near light sources which give out unpolarized light for enhancing this angle of linear polarization map. So how we do this is we use two light sources. So one on each side of the object. Okay, so for example, we turn on one light source on the left side, and then this is the angle polarization that we can measure. And you can see, obviously, on this part, which is this part of the left side of the object is the angle of linear polarization is enhanced by this light source. And then we turn it off and turn on another light source, which is on the right side of the object. And you can see the other side is enhanced. And then by combining these two, we can get a much better angle of polarization map, which is more related to the surface normal. Basically, this rule out the influence of the uncontrolled environment light on polarization state. Okay, and with this, you can do a better normal estimation. So here I just show you comparison with the ground truth. As you can see, this is much closer to the ground truth angle of polarization that is captured under a darkroom setting. Okay. And again, if you directly use this equation for normal estimation, your normal angle is up to a 180-degree ambiguity. And then here we want to combine this polarization constraint with photometric constraint for shape estimation, which eliminates this ambiguity. So here, just give you some background on photometric constraint. What does that mean? So basically, this is something used a lot in photometric stereo, where you have a light source, which you know is lighting direction, which is L. Then you take a picture of the surface, and then you can use the relationship between the image intensity and this normal angle and the lighting direction for estimating this normal, right? So, so in a standard photometric stereo, you will need to have at least 3 equations like this, meaning that you have to have 3 light sources on in order to solve the normal of a surface. Okay. And another assumption of this model is that this only holds under the Lambertian model, which means the surface is perfectly diffuse and follow the Lambertian model. But in many cases, the surface don't have this perfect Lambertian property, and it may have specular highlights. And we also show that we can use polarization filter and polarized light source and with polarization filters to remove that unwanted specular highlights. And here we are using a circular polarized light source. So because it's circular polarized state and it doesn't have the linear state, so using this kind of light source won't affect the angle of linear polarization that we want. Okay. So basically how it works is by using a circular polarized light source and then using a camera with retarder that can measure the full Stokes polarization state, we can do decomposition on the captured image where we separate out the circularly polarized component, the linearly polarized component, as well as the unpolarized component. And here the unpolarized component is the perfect diffuse image that has this relationship between the intensity and the lighting direction, which is good for photometric stereo. Okay, so then we combined 2 photometric constraints. Remember that we have 2 light sources, 1 on each side, right? With the photometric constraint, which is the relationship between the angle of polarization and the surface normal. So we have this linear equation for solving the surface normal. So another thing I wanted to be aware is that the photometric constraint here is actually not good because, again, for standard photometric stereo, we only want to have images that is directly taken under certain light source. But here, because we have a lightings from the environment, that makes this constraints not accurate. And then what we do is to come up with a approximation of environment light, which we call it a light proxy map for estimating the effect of environment light. Okay, and our lighting proxy map is basically a array of light sources sampled around a hemisphere. And we assume that the lighting directions, they're all towards the center of the sphere. And we estimate the intensity for each sample points that are on the sphere. So basically what we do is we first solve this equation and have an initial estimation of this parameters, and then we want to use them to estimate the lighting proxy map. For example, the intensities of this light samples. Okay, then after that, we iterate back into the initial equation, basically by taking out the part that is contributed by the environment light, and only estimate the part of intensity that is contributed by our near light source. Okay, so we do several iterations, and that significantly improved the results. So basically in this equation, this part is the intensity that is contributed by the environment, which is calculated by our light map approximation. And this part is the direct intensity that is contributed by our near light source, which is something we want. Okay, and then back into our original equation, we decompose the total amount of intensity into these two components. And again, this, which is this part, is the intensity that is contributed by the near light source, and this is from the environment. And with this, we can have better estimation. So now let me show you some experimental results. So we do synthetic experiment for quantitative evaluation, because in the real experiments, and many times it's very hard to have the ground truth results. And we use the Mitsuba renderer for the parametric rendering. And again, in order to apply the parametric material, we use the PPRDF dataset that is contributed by Sanhuan. And we try different scenarios. Basically, we use different materials for the object and combined with different environment map for simulating the testing images. And then we apply our method for normal estimation. And here's some results that you see for different scenarios. So you can see the mean average error of the normal angle is around like 7 degrees or something. And this is the per pixel arrow map of the estimated normal. And here I show you the setup that we have for doing the real world experiment. Okay, so basically we have a we have a polarization camera, which is mounted looking at the object, okay? And then we use retarder in front of the camera in order to measure the circular polarization state, because we want to use that for decomposition to eliminate the specular reflection. Then we have the two near light sources for enhancing the angle of polarization. And again, we have filters in front of these light sources in order to create circularly polarized light. And we can move this setup around and take images under natural environment. So here I want to show you the comparison of what happened using the near light source, and how the near light source is going to improve the angle of polarization that is measured under the natural environment. Okay, so we try different indoor and outdoor scenes. And here are the ALLP map that is directly measured without turning on our near light sources. And you can see there's actually a lot of variations of the angle polarization of this object, right? Because this is affected by the polarization state of the environment. And then after applying our near light sources and then the fusion algorithm, this is the refined ALLP angle of linear polarization that we can get. And you can see, if you take a look at this object alone, each of this map, you can see that the angle of polarization of each of these same object is consistent across different environments. While on this one, they are a lot of variations. And again, this variations is caused by the linear polarization component in the environment light. Okay. Also, you can see that environment is actually also polarized. You can see this different angles in there. Okay. So here, basically what I want to show you is by using the near light source and fusing the angle of polarization, we can get much better measurement of angle of polarization that is only relevant to the intrinsic shape of the surface of the object itself. And here I want to show you some comparisons with classical shape from polarization method, which is directly using that angle of polarization normal constraint, and also existing shape transition and plus photometric stereo method. And again, this method, they don't consider the influence of environment light, and they are done in a darkroom setting. And you can see, so this is our method. The first row is our method, and these are the two classical methods. And you can see the other method, as they don't take into the influence of environment light into account, the estimation looks very flat, and they don't quite recover the details of the object. So with the surface map, we can then integrate it to come up with a mesh surface to represent the geometry of the object. So here are some surface mesh results that we have. So with this, I think I show you how to use the polarization constraint combined with other physical constraint for shape estimation. And then I want to show you another example that combine the polarimetric constraint or the geometric constraint that is offered by the angle polarization with another type of classical physics constraint, which is called the Helmholtz stropsis, which is a method that is first proposed by Ziegler et al. In 2002. So the Helmholtz stropsis, or HS, exploits the reciprocity of BRDF of the surface normal estimation, and it has some advantages, which are this kind of method. It doesn't need to assume any non-surface reflectance and can be applied to arbitrary surface material. Remember that back in the photometric stereo, we need to have the Lambertian surface assumption. But here in HS, you don't really need that kind of assumption anymore. But in the classical or standard HS method, at least 3 reciprocal image pairs are needed. So before going further, I just want to quickly give you some example on the imaging setup. So how to do this is that you need to take a pair of images, which is called a reciprocal image pair, by precisely switching the light source and camera position. So for example, if the light source and camera are in this position, I take one image and then I precisely switch their position and take another image. And this gives you the reciprocal image pair. And then in order to do the standard HS, you need to take at least 3 pair of this kind of images. Okay, so let me first briefly, before introducing polarization to this problem, let me first briefly give you some background on why and how this this method work. So this method is based on the fact that light path is reversible. So basically, this means that the light follows the same path when its direction is precisely reversed. Okay, this is a well-known fact, and because this phenomena is first discovered by a German optics and physician whose name is Hermann von Helmholtz, this principle is also called the Helmholtz reciprocity. And if we go back to the BRDF that is commonly used in graphics and vision, this is translated into the reciprocity of BRDF. which means that if you precisely exchange the imaging and light source position, the BRDF value stays the same. Okay, so this is basically the reciprocity principle. So now our question is, does this reciprocity property still hold if we consider the polarization of light? And again, let me just give you some recap of the polarization parameterization, which is already been talked about by someone. So here we use the Stokes vector for representing the polarization, which is a 4D column vector. And then the polarimetric BRDF is again the Miller matrix that associate to Stokes vectors. And a Miller matrix is normally a 4x4 matrix. So here in our problem, the polarimetric BRDF here is no longer a scalar value, but it is a 4x4 matrix. So now the question is, does the reciprocity property still hold? Does the two matrices still the same if we exchange the imaging and lighting direction? And then I can tell you the answer is no, but we have derived another kind of reciprocity relationship, which is called the transpositional reciprocity. So what does that mean? That means when you exchange the light source and camera position, the two BRDF, polarimetric BRDF measured, they have this transpositional relationship, meaning that one matrix is the transposition of the other. So for example, if this M matrix or the polarimetric BRDF measures with VA as the incident direction and VB as the exit or reflected direction, as is shown here, then we have another matrix M, which is measured with VA. Imagine that we exchange light source and the camera position, VA as the incident direction of the light, and then, VB as the incident direction of light, and VA is the reflected light direction. Then these two M or polarimetric BRDF measured, they are the transposition of each other. Okay. So although this is not a simple equivalent relationship, but still they are related. And this relationship is, again, simple enough for us to make use of. So with this, we can also do similar similar setting as the standard address for shape estimation, right? So by exchanging the light source and camera position, we can take two images, and then we also call it the reciprocal pair. But the image formation equation is changed with the Stokes and Muller representation. In the standard setting, they are the intensity and scalar BRDF, right? But here they become the Stokes vector and the Muller matrix. So basically, this equation shows what is the Stokes vector that will be measured by the camera if you have a light source whose Stokes vector is as L, which we don't know, but it doesn't matter because it will eventually cancel out. And there's BRDF of a point right here, which again, we don't know this BRDF term. And this terms rho and these terms are the attenuation that is caused by the distance of the light source and also the incident angle of the light source. Okay, these are very standard radiometry. And again, using the same way, we can formulate another equation where the camera is again here. Basically, we switch the position of the light source and the camera. So with this pair and apply our transpositional reciprocity, we can have an equation that given these two Stokes vectors of this reciprocal pair, how these two Stokes vectors, they are related to each other, and certainly is a function of the surface normal n. Okay. So we further show that with the polarimetric constraint, with the transpositional reciprocity constraint, we only need two reciprocal pairs to solve the depth and normal of the surface that we are imaging, versus the standard method needs at least 3 more images. So then let's see how why we can do this, and how we can integrating the polarimetric constraint, which is the relationship between the angle of polarization and surface normal. So remember that because our light source here is linearly polarized. Again, in the first part of my talk, I show you that linearly polarized light will affect the angle of polarization relationship with normal. Then we do a decomposition of the captured Stokes image to come up with a representation of the angle of polarization, which is perfectly related to the surface normal, such that we can apply this equation for normal estimation. And then I want to show you some example on how this can be improved. So for example, these are some overall images of some object, and then we apply the decomposition to separate it into 3 different parts: specularly polarized, diffuse polarized, and diffuse unpolarized. And with the diffuse polarized component, we can have a much better angle of polarization map, which is directly related to the surface normal. Whereas the overall image, the angle of polarization is somehow affected by the polarization of the linear light source. So, and again, similar to the example that I show you for combining polarimetric stereo and the polarization, here we can combine the reciprocity constraint with the polarimetric constraint for the depth and normal estimation, for geometry estimation. So how we do this is, again, stack them into a linear equation where the coefficients of the coefficient matrix is a function of depth d, and then it multiplies with the normal vector, has this relationship for linear equation. So how we solve this problem, because we have 2 unknowns here. We have depth d and a normal. Of course, normal is a 3-component vector. So how we do this is we first solve the depths. We first optimize the depths using the rank constraint, basically, which is saying that the rank of this coefficient matrix should be 2. We first apply this rank constraint for depth optimization, and then we plug in the depths for normal estimation. And then we do this with several iterations for refining both depths and normal. And normally this is something that will converge after 4 or 5 iterations. And then I just want to quickly show you how we do the actual experiment. So we come up with this rotary plate for exchanging the camera and light source position. And again, we are using a polarization camera here, and we have a light source with filter to create linearly polarized light. Okay, so how to change the position is by rotating the plate by 180 degrees. And certainly everything is calibrated geometrically. So then I want to show you some results. So we do some quantitative evaluation with the real object. For simple real object with known shapes, for example, this billiard ball here, we can measure its diameter and we can know it's a perfect sphere. So we have the normal map of this object. So here's a comparison of our method versus the standard Helmholtz-Strophes, which doesn't use the polarization at all. So if we use 3 pairs of reciprocal images from Helmholtz-Strophes, this is the normal reconstruction that you have. And the mean angular error is around 15 degrees. Well, using our method by considering the polarization, the normal estimation is largely improved. And also we take less number of images, right? But still, there's some artifacts along this vertical direction because there's some degeneration of the angle polarization along these angles. And then how we do better is we take another pair, we take another reciprocal pair, and then this is the result we have. And obviously, we don't have that errors along the oblique angles. And also, the mean angular error is largely reduced. So then we integrate the normal and come up with the surface shape, and here shows the profile of the cross section of that integrated surface. And you can see our estimation is closer to the ground truth. The ground truth is that thick orange line in the back, while others, they are not as good. And here shows some comparison between our method and other shape estimation method, like a structured light, photometric stereo, and shape from polarization. And again, you can see that our reconstruction using two pair of reciprocal images has very good results comparing to this other classical method. It can preserve the surface detail in much better than the other methods. And then here's some experimental results of more complex objects. For example, the statue, and the statue has different kind of materials on the surface. And if you zoom in, you can see that our method, again, using two reciprocal image pairs, can recreate very fine surface details. And here are some more examples of diverse objects with different surface materials. And again, our method is not limited to what kind of surface reflectance that the object has. Okay, so in summary, the main message I want to share with you are polarization is highly relevant to geometry. It's very useful for shape estimation. And by integrating polarization Q, you can combine it with other classical methods. You can have much better quality of 3D reconstruction. And if your polarization Q is corrupted by either the environment light or the polarization state of your light source, you can improve it by either using a unpolarized near light source or by using the image composition that I show you in the second part. And lastly, I want to say that all methods are physical based, which means that they do not require any training. So I want to say that they have the advantages that they don't require assumed priors on the scene, and then also you don't need to have large amount of data for the training. Again, it also has the advantage that the optimization scale is much smaller than optimizing a neural network. Okay, and in our next talk, Achuda will talk more about learning-based polarization reasoning. Okay, so yeah, I'm almost right in time, and then I think that's the end of my talk, and we can take a few questions if there's any. Yes. Yes. So that is because, so let me go back. So that is because if you want to have this kind of like angle polarization map that is related to the surface shape, the assumption is that your light source is unpolarized, such that the reflected light from the surface is only related to the shape of your object. And then if your light source has its own linear polarization state, some linear polarization component, and then that component is affecting the reflected light. So basically the reflected light, the polarization state of reflected light is a combined effect of the state of the light source and also the geometry of the surface. So that's why I'm saying that the, well, actually is, let me see. So basically this equation is corrupted if your light source has linear polarization state. So basically this equation is the equation between the angle polarization that is only related to the surface geometry and the surface normal. Yeah.
So is it only polarization?
Only linear. If it's circular, it's not going to affect it. Only the linear polarized light. Of course, if it's elliptically polarized, then it means that it has linear component. Then it will also affect. Yeah. Yeah. Random. Right. Wait, right. Basically, you can imagine that you have the linear polarization of all directions, and you don't know like at a certain time which direction it will go. Yeah, linear is like vibrating always along that direction. Yeah.
And one of the slides were showing angular polarization estimate, and it seems like we have like the 8 to 15 degree error somewhere. Is there a tolerable error?
So you are talking about a result, right? So let me see. Is this one? Okay. Yeah. So basically, this arrow shows the mean angular error. Basically, we compare the per pixel normal direction to the ground truth, right? And then we take the mean of all the pixels available in this map. Yeah. All right. Yeah. It will be transparent. Yeah, transparent won't work, I have to say, because you have too weak a reflection out of it. Right, that's a good question. If it's very black, then you are not going to have enough amount of reflection. Then yeah, the method won't work very well. Yeah, if it's completely black, I won't see it will work. Yeah, because you need to have a certain amount of reflection out of it.
What if
diffusing will be perfect. That will be very perfect. Yeah, yeah. Diffusing or has some specularity that won't affect our method. Actually, from this example, you can see that this plate here is sort of like specular, and this gel is pretty diffuse. Yeah. Vast signal, I wouldn't say there's a scenario for the best signal. This is because the constraint that we use here. Oh, actually, for not like the cases that I'm not working, I should say that dielectric objects is not working because for this equation, assume that the surface is non-dielectric, meaning that it's non-metal. Yeah, I have to add that. But for like the best cases, I wouldn't say they're the best cases, because as long as it can work, you just work. Yeah. Okay. Yes. Yes. So in both, I don't know if you're talking about this, but in both parts, we are using the linear polarization sensor. And here in this one, we only measure the linear polarization state. But in the other one that I showed you earlier, in this one, in this one, we also put a retarder in front of the camera to measure the circular state, because we need a circular state for the decomposition.
these image sensors cannot measure certain.
Right, the commercial polarization sensor you buy, they cannot measure because you only have the linear polarizers, on top of the sensor. Yeah. Right, you have to put a retarder, quarter wave plate of retarder in front of the camera, and you take two images actually. Yeah, with the quarter wave plate and without, and then you take the difference. Yeah, then you have the circular state as well. Yeah, otherwise your circular state will always be zero. You don't have. Can you repeat the question again?
Two images with linear polarization sensor, one with quarter wave plate, one without.
Yeah.
And then that map the whole degrees of freedom that I have.
Well, I didn't quite understand what you're saying. You reduce the degree of freedom that you have.
So if I just have the linear polarization, I don't measure all parts of the.
No, so with the linear polarization, you don't measure the phase shift. So what a wave plate do is introduce a phase shift, and you take an image with it and without it. That phase shift gives you the circular state. Yeah, but the linear component won't change.
No.
Yeah.
But I'm just wondering, what do I need to get the full polarization information?
That's how you do it, right? With the sensor, commercial sensor, you get the linear state. Basically, if you map to the Stokes factor, you have S0, S1, and S2, but S3 is always zero. And then if you put a retarder, quarter wave plate retarder in front of the camera and take two images and make that subtraction, then you have the fourth component, which is S3, and that gives you the full Stokes. Yeah. Okay, so it's a little bit over time. I think we just stop here, and then I'll give you some time to enjoy the coffee break, and then we'll come back at is it 10:40, right? I think it's 10:40. We will come back at 10:40, and then Atuda will give a talk about polarization and deep learning. Okay. What? Oh, yeah. Maybe. Forgot. Maybe either you or George can announce. I mean, the launch.
Yeah, sure.
Yeah.
So,
But how do they go? They just hey.
hi. Let's see if Oh, okay. No problem.
Virtually, yeah. We have a. Yeah, I just talked about that. Sorry,
Well, anyway, get ready for Friday.
Oh, yeah. Flying song. I'll be home. So, yeah.
Yeah, you need 5.
Oh. Oh, thank you very much.
Everything else is so I don't know if it's
Oh, yeah. I didn't check.
Well, it's not even in the
Maybe we can see that.
I can, but I'm gonna check every single thing.
Oh, yes.
And that's and other reviews. Yeah.
No. Yeah.
Yeah, I hope that's 3 hours.
Okay.
So I'm sure that. Friday. I don't know how many that's. I selected those 2 hours.
I'm just worried, like, if I'm going to have that huge. Let's say.
Yeah, I think it's okay. Oh, no. Oh, you hear those? The trains.
Yeah, actually, I have to do this or some friends. Because if my kid is not cheaper, like, then I hope yeah. Although I'm not doing that, then there's a cheap, like a cheaper, like actually like actually I'm just like. Yeah, yeah.
Does the
Yes. Yeah. Well, last year.
Yeah. Yeah, I think it might be just being there.
Yeah. Hey, you tested? No, it's okay. Why don't you? Yeah.
Are we, so I'm
Sorry,
sharing my
sorry.
screen.
Uh,
Yeah, so I'm sharing my screen, and
Yeah.
projecting here. Is everything good? Is it recording audio?
yes, I think the recording is always on. And do you want to try? Maybe let me. And I'll take Archman.
Perfect. Yeah,
Yeah,
so this should
that's a
work, yeah.
good view, right?
Yeah, that's a great view.
Okay, good, good.
And, oh yeah, so then I can get started then.
Yep.
So have you timed your slides? Have you timed your slides?
Actually, no, embarrassing, I finished like last minute, so I.
Because I noticed that, I don't know, are you gonna use all the 45 minutes?
I can be sure.
Okay, so I'll try to keep in mind to time, but just in case I might go like 5 minutes over or something, so.
Yeah. So have you joined the meeting? I think you need to join the Zoom meeting. Yeah. So, yeah, let me, I think I can hear John.
When we were taking QA, basically, George, what you can do is, I don't know if this helps, but just come around to this side. If you're sitting here, for example, you could be the next, actually, you can sit up here
Okay,
because you're speaking next. You just hit Apple I, it'll give you the number and then the passcode.
I'll just use this computer to.
No, just present from,
No, you can use, well, if
Just
you want
join.
to use the computer, you can like airdrop your file to this computer.
Okay, I'm
Yeah.
gonna use the Google Slides.
Oh, Google Slides, okay, then just use a browser here.
Yeah.
I think.
Okay.
Yeah,
that's
yeah.
easy.
that's
That's
easiest,
easier.
yeah.
Yeah. Well, the Google Slides, can you, I don't know, they have the presenter view or, but I can mirror it or something.
I give the business review, so I have them.
So do you want to check on here? So let me just Okay, so our next talk will be given by Achuda Kandafi, assistant professor from UCLA. They will talk about deep learning and polarization. So while Achuda is testing the connection, I'll give a brief intro of Achuda. So Achuda is assistant professor at UCLA. He received his PhD degree from MIT in 2018. He has received many prestigious awards, including the NSF Career Award, DAPAR Young Faculty Award, ARO Young Investigator Award, and the Forbes 30 Under 30 Award. He has co-founded several startups in computational imaging and computer vision, and he has co-authored a textbook called Computational Imaging with the MIT Press. Okay, so Achuda, now you're good to go.
Great. So thanks a lot for having me here. It's a privilege to follow such excellent speakers. I think the trajectory of this course kind of, I think it's the way it's organized. You know, we had some very fundamental talks from my colleagues, Sang-Hwan and Jinwei. Then I will start kind of bringing a little bit more of deep learning and applications as well into it. And then the closing talk by George is going to be very application focused, showing some real world results at his company. There's also a quick announcement that at 12 noon, which is at the end of the tutorial, there's a networking lunch, and I think George will chime in more about the details on that. Okay, so let's jump in. So the agenda for this this particular talk is twofold. So one is we're going to talk about physics and ML, kind of in a very broad sense, and then we'll apply that we'll translate those ideas to polarization. So, what is physics-based learning? So there's a lot to unpack there, and kind of a lot of opinions on what physics-based learning is. We had a recent article in Nature Machine Intelligence with my colleagues, including Stefano Soato, who's also here at CVPR. And basically, we kind of summarize a few different areas of physics and computer vision and the way this is being incorporated. Now, the first step is that incorporating physics into vision is hard. As you heard from the previous talks, there's a lot of physical models that are there. And the challenge is that neural networks are typically a black box. So it's very hard to put like structured laws into something that is inherently a black box and designed to crunch data. So I think there are three broad ways to blend physics and learning that you know we're kind of seeing. Kind of the first way is this sort of well, let me start from here, which is the physical fusion. So this is kind of one method. And in the physical fusion method, you basically think of, you have your input, which could be like images. So you could have like images here. And your physical information could be maybe some operation on those images. So it could be like rendering. So like in the case of polarization, your input could be like the raw polarization images. And then your physical information could be like the shape and polarization data that you put in, right? From Sang-Hwan's talk. So now you would put in the SFP data as features, and then you would just essentially just blend them in sort of like a multimodal learning framework. So think of physics as just another sensing modality, almost. So that's kind of one method of blending physics and learning. A second way is if the physics maybe is very good, very, very strong physics, and you're directly predicting an output, then what you could do is you could use a skip connection. And that way you're very strongly preserving the physics, and you just skip it out to the output or something close to the output layer. And so this gives you very strong physics, physical inductive bias to your model. So an example of doing this would be like if you were trying to predict projectile motion, this would probably be a good model to use, because you are going to skip your parabola equation of tossing a ball all the way to the output. And that's kind of a good thing to do to preserve that information. A third way that we're seeing is to use this hybrid latent space. This is very popular in methods like NERF, Siren, and so on, where you're kind of representing this data. And the idea is to regress some quantity that could be physically interpreted. So for example, NeRF is regressing essentially color and opacity, which can be physically interpreted vis-a-vis volume rendering, as an example. So that gives you this hybrid latent space that you're regressing, which can be interpreted by the neural network as having a loss, but also in terms of the physics of the problem. So these are three broad ways of blending physics and learning. And as you can imagine, they have their benefits and limitations. Now, this isn't a course about physics-based learning. This is not such a course, but there are benefits and trade-offs to which ones. You kind of hinted at that when I talked about the skip connection here. Like if your physics is really good, you'd use this. If your physics is not as good, you'd probably use this. All right. It also, categorization is also kind of always an issue, right? When you categorize things, the lines are blurry. So you could also combine different ideas from different motifs here. You don't need to like be in one of these three buckets. You could combine different types of areas. So here what you're doing is you're using residual physics here. So you are using that skip connection of physics, but rather than skipping it to the output, skip it somewhere at some intermediate feature layer and then still do the fusion at those feature encoding layers. Okay, and if I look at NeRF and similar methods, just to put it really concretely, I'm not sure these are the best colors. This is what happens when professors write their own papers. But anyway, you have this color here, which I don't even know how to describe it, maybe like beige. This color here is kind of supposed to be a mix of red and green. And so you have this mix here, where you have this hybrid world, where if you think about your data-driven world, you want to regress something, rather than going and regressing something that's not interpretable, regress something that you can really interpret. And I think NeRF did a beautiful job of this, of saying, I'm going to regress opacity and color, because you can interpret that inside the physical world. What that gives you then is it gives you a hybrid loss as well. You could have your annotation error of how good you are at predicting these two dots here. And so your total loss, L total, would be like L annotation from this figure, plus L1, plus L2 from physics, and so on, where we have kind of even like K physical interpretations of these quantities. It doesn't even need to be one, which is the volume rendered. You could have K physical interpretations of something. And so that would give you this kind of hybrid loss function. Okay, so if I look at examples of this hybrid loss, we have neural rendering from the NeRF paper. We also have a very nice paper called Siren that also kind of looks at this very similar implicit function philosophy. Okay, so this talk is going to cover primarily two themes. We're going to be discussing a lot of physical fusion methods, which was one of those architectures. And a couple papers here are deep SFP and SFP in the wild. And then we'll discuss hybrid functional methods, which draw from the implicit neural representations. And here are a couple papers. So my colleagues have given a pretty good overview of what shape-front polarization is. I'm going to kind of drill down a little bit more into it. So at least we leave this tutorial with a clear understanding of what SFP is. So SFP, basically, polarized light reflects off an object and gives you the shape. That's the basic idea. Okay. It's a powerful cue. So on the left, we have the depth from a Microsoft Kinect. This is the 3D shape from a Kinect. It's kind of like noisy. If you add these three photos using a polarizer and the SFP equations, you can get this as your reconstruction, which is a much stronger and enhanced version. So this is a 2015 paper before kind of deep learning really grew into these problems, but you're still able to get pretty good results. The problem with papers like this, or at least this paper, is that there's pretty strong physical assumptions that are being done. Hyperparameters, for example, due to the physics of the problem. Setting your refractive index of the material, for example, you need to actually plug that in or hard code a value to start getting these type of results. So let's go through the SFP problem in maybe just 2 or 3 minutes of detail. Okay. So what is the SFP problem? Here I have a shape, which is some object which has a curve here, and it has some refractive index n inside the object. Outside the object, you have this vector n, which describes the shape or the slope orientation of that surface. Okay. So our goal here is to get this quantity vector n, which is going to give us the local geometry of the surface. If we are able to get that quantity vector n, it's going to be great because then we can just have a curve and we've got its gradient and we can integrate that gradient to get the topology, right, of the curve. Now, if I look at how SFP works, the canonical theme of SFP is you shine light at some angle theta here. By the law of reflection, if this is theta, then this angle also equals theta for specular reflection. And you're going to shine light here, and light's going to bounce off, and your goal is to solve for this angle theta. Now, the problem is that just laws of optics and Fresnel reflection tell you that some light is going to go inside this surface, right? Not all the light will be reflected from the surface. Some light will be absorbed, and the absorbance will occur if you have kind of a single scattering event at some angle theta prime. So theta prime will kind of go into the surface. Now, to make this even more complicated, each of these line segments here has a polarization state. So I'm going to draw that with dots and hashes, okay? So if I think of a ray like this of light, the dots along the ray are like arrows pointing out of the plane of the board. So what that means is that the light is oscillating. There's an EM wave of oscillation that's oscillating out of the plane of the blackboard. And that's what these dots mean. So the hashes, conversely, mean that light is oscillating within the plane of the board. So what a ray like this is telling you with dot and hash is that light is oscillating both in plane and out of plane. And so you have essentially both horizontal and vertical polarization on that ray. That's what that's telling you. So now, if I have this horizontal and vertical polarization along the ray, I might just have a scenario where the polarization that comes out is just out of the plane of the board. Okay, so vertical, this would be S polarized light. So I have S polarized light coming out of the plane of the board. Now, what might go in then is mostly horizontal polarization into the plane of the board. And so if you look at this, each line segment here has a different polarization state. Each line segment has kind of a different angle, and it's starting to get a little bit complicated. Okay. Now, luckily, we have these equations from optics to describe this effect. So the equations that describe this effect are known as the Fresnel equations. So it's kind of an old principle. It's from the 1800s, but it basically tells you that this angle theta somehow corresponds to the reflectance of perpendicular and parallel polarized light. Okay. So this is your equation. So if you think about what the shape from polarization problem is, it's kind of like this. You know, you've got measurements from the polarization cameras that my colleagues Jinwei and Seungwon mentioned to you, which is the reflection of perpendicular and parallel. So you've got those. You might have some hard-coded value of the refractive index, which I kind of mentioned offhand in the 2015 paper. And based on that, you can solve for your theta. So you can just do an algebraic solution for theta, and that's going to give you essentially the same. Now you can start to see how many assumptions there are. First, you need the refractive index, right, n, to solve this, right? I just circled this refractive index in green, but it's really a red quantity because you need it, right? How are you going to get the refractive index of an object? You know, objects around us have very different refractive indices. And in addition to that, I've only drawn one type of reflection here, which is a specular reflection, kind of mirror-like reflection. There was a question in the QA about diffuse reflections, for example. How would it work on a diffuse reflection? How would this model work? It's actually a very different physical model, and it makes some pretty strong assumptions of how light reflects. Okay, so what's the bottom line here? The bottom line is a tricky problem, but I'm going to show you just the result that's captured on an elementary surface to give you some intuition of the problem. This is a pool ball, like you know, the snooker pool, and you've got the pool ball, and you've gone and painted it with diffuse paint. All right, so it's a pretty diffuse object right now, and what's being done here is multiple photos are being taken at different polarizer rotations. So 0 degrees, 10 degrees, 20 degrees, 30 degrees, so on and so forth. So you've got these multiple rotations, and I can pick a point here. So for example, you can pick this blue point right here. Okay, so you pick this blue point right here, and you can plot the blue point as a function of the stack. Right, this stack here is along the axis of polarizer angle. Okay, So if I plot this blue point along the stack, I'm going to get actually this curve. This is the real curve actually that you get. It's many images are averaged, so it's not just one picture. So at every angle, multiple pictures are averaged to give a clean curve. But you can get a pretty clean curve here, where you have a very nice signal. As you go along polarizer angle, you have this very nice oscillation here. Okay. So if I were to now go and pick a different point on the sphere, so now this red point is chosen here. So this red point, if you plot it as a function of the polarizer angle, you actually see that there's a phase shift here and there's a change in its amplitude. Okay. And this is interesting, right? Because now it's validating what we had about geometry earlier. Meaning if I look at this blue point and the red point, what's the difference between the blue and the red? Well, if we think for just 30 seconds, right? Same object, same material, same lighting conditions, broadly speaking, it's a sphere though. So because it's a sphere, the geometry is different at different points on the sphere. So if I look at this sphere, these 2 points have different geometry, and as a result, there's a different signature in the polarization. Okay. So this all looks pretty good, and you end up with this equation. This is the transmitted radiant sinusoid equation in polarization literature, TRS. Okay, so this is the TRS equation, and you can see kind of already that this describes, it's basically a cosine with some constants, but you can already see kind of a goal here, right? It's a cosine with some phase term, and you want to solve for the phase of a cosine. And the nice thing is you can sample the cosine because you can sample different polarizer angles. And so when you sample the cosine and you solve for this, it seems like you would be able to get a good estimate of geometry. Unfortunately, there's another problem. The problem is that there's a factor of 2 here. So if you have 2 candidate angles, phi and phi prime, that are off by 180 degrees, then you're going to end up with the exact same brightness measurements. So you're going to have a problem of ambiguity. So just to be concrete about how this would work, if you're doing straight from polarization, and I have a surface, like imagine I have the camera here. So here's the camera. So if I have a wall that is pointed this way, it's actually going to appear identical to a wall pointed this way, because what happens is the azimuth angle of these two is about 180 degrees apart. Okay. So bottom line, the kind of take-home message here is that shape from polarization is an underdetermined physics problem. You need to know the refractive index, which we just talked about. You have this pi ambiguity in the surface normal, which we just talked about. And then you also have low SNR. And then, again, similar to the question that was asked earlier, the surface needs to conform to a nice reflection model. Okay. All these factors taken into account, this becomes actually a pretty difficult problem to solve. Difficult also means that results are not often easy to get. Results are not great, in other words, if we use physical models alone. So here's an example. Okay, this is a result on a real-world object. Now, this object has mixed material. Okay, so it's got like, the beak is painted a different color, black, red, white, pink. And because it's a different color, different paints are used. Different paints have different materials. Different materials have different refractive index. Okay. So the different refractive indices are now showing up here, where you can see kind of material artifacts showing up. For example, there's no reason that this crown should have such a strong contrast from the paint, but it does. There's also no reason that the shadows should be causing artifacts, but they do. So there's a lot of these kind of image-based artifacts that are not polarization-based, that propagate into the geometry, and we call this problem as a problem known as texture copy. Okay, so if we use the Fresnel physics alone, we also end up with 42 degrees of angular error. That means that the surface normal that we estimate is 42 degrees off on average. This is not good. So typically, photometric stereo will have which is a very good shape method, will have 5 to 10 degrees. So that's that's ideally what your target should be for really high quality capture. Now, this is a paper in 2020 that's doing deep learning to address this problem. You can immediately see much better results here. You can see that you're preserving the contour. It's very difficult to identify material-based artifacts. You can see that the shadow along this ridge, there's still some artifact, but it's minimized. And so this is kind of a much better result. And you can really see that if you compare it side by side. Now, of course, I must also really present for some balance here that this paper that is doing the physics-based work is also done in 2003. So there's a lot of knowledge that we've gained since then. But the primary difference between these two, since the Miyazaki paper, has not actually been advances in better physics, but actually the data-driven revolution. So if I look at that result with the coffee cup earlier, it was sidestepping the problem by using depth information, but these methods don't have access to depth information. This is purely surface normal based. So this is the architecture for such a network. And you can see that this is really physics fusion, right? Basically use physics as just another sensing modality. So you take your raw images as input from one sensor. You can call this as sensor one, and then you can make a virtual sensor, VS2, right? This virtual sensor is basically going to be where you take the images and then you apply some sort of physical prior, and then you feed those both in, and you find some common feature space to do that. Okay, so kind of very simple encoder decoder to get these types of results. So the data is available at the author's website. Basically, a scanner is used to obtain 3D geometry, single shot polarization camera, not unlike what colleagues were talking about earlier, and then some classic computer vision of 2D, 3D registration. The data set, how do you select the data set is important. It's really important to have mixed materials in your data set. You can see this snow globe is kind of shiny. This is a little bit more diffuse. The paints are different. So you want this type of variety in your data set. And of course, you want lighting and indoor outdoor scenes ideally. Now, for the deep SFP paper in 2020, this is all object level. These are all single objects. These are not scenes, which have depth discontinuities and more complex things to handle. But this is 2020. So then in 2022, I believe there's a typo here. This should be 2022. Lei et al. From Vladimir Colton's group in Intel had come out with this paper called Shape from Polarization in the Wild. And essentially what this paper is doing is you take a raw polarization image, very similar to what Deep SFP is doing, but there's some nice tricks here beyond just shoving it into physical fusion. There's some better pre-processing, like a view encoding embedding. And this is a really nice idea that is saying that, look, if you want scene level understanding of shape, then you need to take into account perspective, because a wall is going to have a different slope depending on if you look at it close or if you're further away. Those types of discontinuities become very important when we can't assume a single object at some orthographic perspective. And so based on that, the authors are able to get very nice surface normals here. This is kind of like a screenshot of their estimated normals. Now, to prepare this type of data, scene level data, they were able to use some of the deep SFP data, but really they had to collect new data. So they used the structured light scanner as ground truth, like an Intel RealSense, and then did co-registration. Now, one of the issues with doing that is that long-range scenes would not be captured. You can't use an Intel RealSense to get the ground truth shape of a building, right? So the authors did have a nice, cool results in their paper where they're actually showing buildings and cars and stuff that are kind of out of distribution in terms of what you capture, and you're able to generalize to get shape here. So these are pretty good surface normal results. You can see that the very strong contrast here between the walls of the building are really nicely picked up in the result here. Okay, so this is shape from polarization in the wild. Now, in 2022, the next conference, which would be ECCV in 2022, there's a very nice paper by Dave et al. Looking at essentially neural rendering, multi-view, and shape from polarization. Kind of a mix of a lot of different ideas, so we can unpack it a little bit slowly. First, what they're doing is they're realizing that polarization images don't need to be captured from one viewpoint. It can be captured from K viewpoints. So there's this multi-view aspect to the problem. So you have multi-view polarization images, and you can use the same snapshot polarization camera that's getting 0, 30, 0, 45, 90, 135 angles. And then you can regress quantities that can be rendered. So there's this idea in the paper of using differentiable rendering. Ideas that definitely predate NeRF. It's a very classical idea of differentiable rendering, but used very prominently in NeRF and neural rendering methods for sure, and used to great effect here by Dave. And what they're able to show now is really pretty cool results. Much better surface normals and geometry, the ability to separate diffuse and specular. So one of the common applications of polarization, I think, probably Dr. Chen from Bayou might show later, is diffuse specular separation would be something that he would show. That's a very classic application of polarization, and applies to autonomous driving scenes where you have like an oil slick or you have ice at some angle, especially in a oblique angle. And so Dave is able to show, using polarization, very nice diffuse and specular separation. And then because there's a multi-view geometry and a volume that's being rendered, they can also show rendering of the owls, for example, in this case, at different views. So this paper was written at Rice. I suppose that's why they use an owl. That's the mascot of Rice University. But so they're able to actually show different views of this owl that's being rendered. So here's their architecture. It's kind of a little bit hairy to unpack, but actually it's quite a simple and elegant concept. The idea is to basically to regress. It's not any dissimilar from the early slide that I showed about the hybrid kind of world. Okay, so there's this, when you do physics-based learning, you think you need to live in a hybrid world where whatever you regress, you should be able to interpret. That's basically the idea. Anything you regress, you should be able to interpret with physics. And so it just so happens that this network looks complicated because the polarization physics are complicated. So there's a lot of different quantities that are being regressed. It's not as simple as just regressing color and volume for opacity and color. So for example, what's being regressed here is they have a diffuse network, which is specifically regressing the diffuse radiance. They have a similar network for specular radiance that's regressing specular radiance. You just understand what the environment illumination is looking like. And so what they're able to do is they're able to regress for each Stokes vector angle, S0, S1, S2. They're able to regress a quantity and then re-render the Stokes vector images. So they're operating on that level where they're actually re-rendering the raw polarization frames, 0, 45, 90, 135, but packed into a Stokes vector. Okay. So they're able to re-render that with respect to a Stokes vector. That then gives you essentially a loss. And if you differentiate that, you start to get very good estimation of these primitive quantities, diffuse, specular, geometry, so on and so lighting, so on and so forth. All right. So the next segment that I'll talk about is even more optically challenging surfaces. So we've talked about shiny objects. We've talked about really good depth. Let's think about transparent objects. Transparent objects might be one of the hardest things to essentially handle with computer vision. So let me start with this motivating question. How many glass balls do you see here? Take a look at the figure and count how many glass balls you see. Anyone has a guess? 8? 5, okay. All right, so actually it's neither 8 nor 5, it turns out to be 1. So there's only one glass ball in this photo. And that's because it's one glass ball on a printout of multiple glass balls, okay? So if you actually look at this polarization photo, you're able to, because you're getting the geometry, you're getting essentially 3D features of the object from one monocular viewpoint. So now what you can think about doing is segmenting that. So not unsurprisingly, if you use like mask CNN, in the intensity domain and try to segment this grayscale photo, you're gonna end up with very nice segmentation here, but there's nothing you could do, right? Because this is the input image. You don't have anything else to regress on. Here, if you do the segmentation on a polarization photo, you can accurately get this feature. So this is a paper from CVPR 2020 called Deep Polarization for Transparent Object Segmentation. And so the basic idea is that transparent objects lack texture in RGB, but they mimic the texture of their background, right? So if you look at these wine glasses, where they are transparent and don't have the liquid, they mimic in some ways the texture of their background. Now, in general, that doesn't work for us, right? Because backgrounds can vary. And so if the transparent object just took on the texture of the background, the network would just learn the background. And then if you try to regress on all the different variations of backgrounds, then you're going to get nothing because there's no common feature. Okay. So our goal will be to get the segmentation of these glass balls with let's pick like a leopard skin background. Let's put like a leopard skin background and have these glass balls in front of that. That'll be the tactical goal. Now, what's going on here is that in RGB, they don't have texture, but it turns out in polarization, there is texture to these wine glasses. So if I look at these this is now real images, no more printed balls here, but these are all, there's actually like, I think there's about 3 balls here that you can kind of see in the RGB image. Okay, 1, 2, 3, and there's a glass here as well. And so if I kind of look at these scenes, and you kind of pick a patch, it turns out that if you look very closely at the edge here, so we can kind of see it, right? So you can very gently see the curvature. You can very gently see it right here. You can kind of see the edge, but it's mostly lost in the RGB. Now, if I look at polarization, you can actually see the edge pretty strongly. Okay, so you can see that kind of line right here that goes down here. And so if I were to plot this as a cross section, you can actually see that the object is kind of there's kind of a much stronger edge in these quantities called AOLP or DOLP, the angle of linear polarization or degree of linear polarization. These are just fancy words for like the phase or amplitude of the sine wave, right? Polarization is sinusoidal in nature, so how strong it is gives you the amplitude. So that's every pixel of DOLP is giving you how strong polarization is. AOLP is giving you the phase at every pixel. That's basically what it's giving you. So whether you take AOLP or DOLP, which is red and green, you're going to have a strong edge profile. If you look at the intensity edge, it's basically flat. So if you look at this intensity edge, which is in black, it's completely flat. Okay. So end result is polarization makes transparent objects a bit edgy. So now in the paper, one can inductively bias the CNN for polarization. So here attention is used, a special attention block that's polarization based. So it can draw features from the intensity AOLP or DOLP in some proportion depending on the type of object. So this is an example of segmentation, of transparent instant segmentation. You can see diverse objects being segmented. The first row, so the second row here is effectively the polarization, right? And then the bottom is the ground truth. So here, for example, we're playing that game of printouts again. So we're printing out transparent objects and showing it doesn't work, or putting the transparent objects in front of a crazy background. Here, this is like a leopard skin print, or like a highly textured rug. And you can see that about half of the transparent objects are not detected in the RGB image. Okay. And one application of this is robot bin picking, where you need to be very accurate with every pick. So you can imagine having these balls, and you could do robot bin picking of these objects. So when you have attention, you can also interpret these attention weights and see if they're picking up the physics of the polarization, right? If polarization is really useful to segment this transparent glass, then you would expect that the network would draw from the input data from polarization more. And you can clearly see that the network is spiking on the DOLP image. You have very high attention weights on a degree of linear polarization image of this kind. So it's just underscoring the value of using polarization as an input modality to the data. So this is a video I decided to use my iPad. It was a choice between playing video or doing the annotations. I felt the annotations is better. And so the video won't play, but here what the video is showing, there's about 8 glass balls here. One is colored. So you can pick up the glass balls easily, all of them, with this polarization camera. So this gripper is then picking up glass balls and then dumping them somewhere else into another bin. Okay, so this is a paper at CVPR 2023, so this year, on neural rendering for AOLP and DOLP representation. So we had some very exciting papers come out earlier. Siren as an example, and then a follow-up work on Siren called Acorn from Lindell et al. And if I look at these papers, what they're doing is they're using these sinusoidal representations of scenes in neural fields. But one of the challenges with neural fields is sometimes it's difficult to get perfect reconstruction of detail, especially when you have high levels of noise in the data. And so one of the ideas that was kind of being discussed is learning different representations. So for example, instead of learning the intensity of this image alone, intensity can vary a lot. Can we learn, for example, the Fourier transform of the image? So rather than regressing on RGB colors, regress on the Fourier transform of an image. It turns out that it doesn't work because there's even more noise, at least in experiments that were done. There's even more noise in the Fourier transform. When you take a forward and inverse Fourier transform, that causes noise propagation. So therefore, regressing directly to Fourier transform coefficients is not the best strategy. However, we did find out that doing low rank approximation makes a lot of sense. So regressing the SVD of an image. So if you regress the SVD, singular values directly with neural rendering, then you can get better results. This applies particularly to polarization data, but also RGB. This result is from RGB, but the paper is called polarimetric coordinate networks, because the value of this really shows up in polarization data even more, given the noise that you have inherent in AOLP and DOLP. Okay, so we are at about 40 minutes here. So with that, I'm gonna pause a little bit early for questions. There's a few papers that were discussed here in this particular talk, and happy to take questions. Yeah. Okay.
I don't think I need the microphone. I'm very loud anyways. I had a question about sort of the beginning of the talk, but it's relevant, I think, all the way through, which is that, especially with the examples of, okay, let's get normals just from assuming we have all the physics and look, we have paint on this thing, practically that doesn't match out, everything breaks apart. When we went from that to the sort of deep learning approach, let's add some other mechanism to it. The Flamingo got a lot better, but you can see that like a lot of some of the normal texture actually got worse. So, like the really fine stuff gets kind of blended into its neighbors. And I think a really big thing you run into any sort of like trying to put physics or like trying to combine your like physics and learning, whatever you want to hybrid model, then you get regression to the mean. Like if you slap a UNet onto your whatever model you have, one of the best things to do is actually just start averaging things together, because you just don't have accurate visible measurements for everywhere in your scene. So with that like preamble, like how do you avoid regressing to the mean in these sort of physics driven problems?
Yeah, I think that's a great question. So let me play it back to make sure I understood correctly. I think the question was in these deep learning methods. So the person who asked the question, Ilya, is noticing correctly that the high frequency texture of the Flamingo is a little bit lost, even though the overall result seems to be better. Some of the sharpness of this is lost because of effectively regression to the mean, where deep learning is trying to learn the average over a data set of input images and shape. How do you keep the sharpness in when you're trying to use a data-driven technique? Is that?
Yeah, and like more general, like how do you? I think I work in the space like not really normal polarization. I work in just like structural promotion. And the other things are a problem. Like you have some really good features that have really nice like matches. And you get great depth of them, and then everything else is kind of stuff in between it's rubbish. But like, how do you keep the stuff that you have the good physics on and blend that with the stuff that like and then like fill in the gap for what you don't have good follow on.
Yeah, okay. So let me answer the question first with the high frequency detail and then second with more general. I think when we wrote this paper in 2020, this was actually at ECCV. So this was kind of like around the time NERF was being written and submitted. And I think that what if we were to rewrite this paper with the knowledge in hindsight, there are ways to take advantage of positional encodings, for example, different changes to the architecture, maybe regressing different frequency bands of the image as well to force the network to learn high frequency detail. So that would be kind of one answer is I think positional encodings have shown us the way to that. Now it's not a solved problem for sure, but I think that would dramatically improve the sharpness of these results. So that's kind of one answer. More generally, how do you keep kind of the goodness of physics and the goodness of data and kind of make it 1 + 1 = 2, rather than having their strengths and weaknesses just mix? That's a good question. And I don't think we have a clear answer on that. Just like any regularization problem, if you think of physics as a regularizer, there's always a balance between the regularizer and the fidelity term. And there is that balancing effect. So I don't know, to answer your question with it, I don't know. I don't know how you would get like kind of a free lunch of being exactly specific to get the best of both worlds, but there are ways that you can help optimize for that. For example, in areas where you know physics is going to be good, for example, if you knew physics, just to use this problem, was very good for the high frequency texture, learn the low frequency with more deep learning, and then learn more of the high frequency with the physics-based approach could be one way of doing it. Yeah.
Great talk, by the way. In the last paper that you were talking about, where you were learning a low rank approximation of the images would change, were those on individual images, or was that on the entire set of images that you saw?
Yeah, so this paper will be discussed Thursday, I think morning. And in this paper, it's an overfit. So basically, it's like Siren or NERF, where you're not learning different like generalization. So you are overfitting to one particular image. So you're given this image of this kind of like pot with sticks in it. So you're given that image, and you want to represent that image as accurately as possible.
Oh no, my question was, you said something about like you don't learn the image directly, you learn a different representation. In your case, that's
Yep.
Did you also consider like because like the SPD of natural images was close to low, but also like the rank of actual images are low. But like if you like stack the images together, the SPD of that is probably the SPD of that is also pretty sharp. So you consider that as well?
Yeah. So what's being happened is that I don't know if I fully get your question, but agree with you on the SPD having some low rank properties. But what you're doing here is think of a set of, given this as an input image, let's call this input I. Given this as an input image, this input image is a sum of different spectral bands. I1, I sigma 2, I sigma 3, and so on, all the way up to K. Okay, so there's K singular value images that make up this image decomposition. And so what's being done here is that a separate network, a separate coordinate network, is learning each of these singular value images. Okay, so you're learning each of these singular value images with the network, and then you're just summing them up. So once you've learned that implicit function, f of theta, you can put a coordinate and your singular value in, then you just sum up over the singular values to get your reconstruction. Is this kind of responsive to the question?
Yeah, we can also.
Yeah. Yeah. So camera lens will have some effect on the polarization, but actually not much. Not much given the essentially small angle aperture that you have typically with most cameras. I don't know how this would play out with a very extreme configuration like macro photography. That would be an interesting experiment to try. Okay, so maybe I'll take one last question while George is setting up. So George, if you want to set up. So then I'll just announce that there's the lunch thing that George can expand on. That'll be at 12 after this. For anyone who wants to join. I think there might be some link to sign up, but let George expand on that.
Okay.
Would you turn on the video?
Yes, it's over here.
You turn on your video?
Good.
Yeah, video here. Yeah, so I can see it.
Okay.
Yeah.
Yeah,
Yeah, maybe as George is setting up, I'll give a brief bio of George. So Dr. George Chen is the computational imaging lead at Value Robotics. His team aims to use novel imaging techniques and apparatus to improve the perception of autonomous vehicles. But before Value, he was a senior researcher and the manager at SenseBrain. He earned his PhD degree from Rice University in 2019 and his BF in imaging science from RIT in 2013. And George will talk about enhancing real-world robotic perception using polarimetric imaging.
Thanks for the introduction. So hi everyone. My name is George Chen. I'm a computational imaging lead at Value Robotics. We are a Bay Area startup company focusing on building foundational model for sensing and mobility. Today, I'm very thrilled to be here to tell you about some applications of a polarized-based computer vision in robotic perception. Compared to the previous sections, this section will be hopefully less intense. We will guide through some of the cool results or maybe not so cool results of polarization, and hopefully it will convince you to explore more using polarization in your perception tasks. So we'll explore the application of the polarization in robotic perception, which I've categorized into 4 primary areas: navigation, visibility enhancement, scene segmentation, scene semantic extraction, and our ongoing efforts on polarization-based depth perception data sets and models. So let's set sail with probably the earliest application of a polarization, navigation. So historically, Vikings refer to the mythical sunstone to navigate the seas on cloudy days when the sun was obscured. It's believed that the ancient technique of the navigation was made possible due to a unique polarimetric property of a type of stone, which sought to be calcite. So our modern day polarimetric imaging sensor could well be considered as the digital sunstones. Here we have a degree of polarization, angle of polarization, and intensity image shown in the slides. I've also marked out the approximate position of the sun around the intensity image. You can see in the highlighted area of the AOP image on the top right, how the skylight's AOP changes based on the camera's heading angle relative to the sun. Several recent studies proposed method for estimating the heading angle using skylight polarization. This figures illustrates the geometric parameters involving a relay scattering model. O here represents the observation position, while P indicates the observational direction in a celestial sphere, with gamma as the zenith angle and alpha as the azimuth angle. And then S symbolizes the sun's directions in the same celestial sphere, with gamma S as the zenith angle and the alpha S as the azimuth. The AOLP is a function, as you can see here in the equation here, is a function of both the zenith and the azimuth angles of the sun's and observation direction. Hence, with the known AOLP, we can solve for the heading angle. So in this 2022 work by Coutier et al., a real-time on-vehicle system based on this principle was developed. The system requires polarization image data, calculates the Stokes vectors, and then consequently DOLP and AOLP, and performs simple image processing on the AOLP image. And then they were able to divide the heading angle. And such proposed system was able to achieve an error margin of a few degrees compared to the ground truth data from a GPS and INS system in the real world scenarios. Okay, now let's move on to our second category, enhancing visibility using polarization-based vision. Let's first look at glare. Mitigating glare is a very important topic because study have shown that there's a correlation between glares and traffic accidents. In a 2014 work, the author studied more than 100,000 accidents in conjunction with the vehicle heading angle with respect to the sun in Chiba Prefecture in Japan. And what they have found that is that the accident rate significantly increased above 25% when driving towards the sun under good weather. And the accident rate also peaked, is also related to the sun's altitude angle. It peaks during the morning and evening hour, which happen a lot of times coincide with the rush hour. When the sun's altitude angle is between 10 to 20 degrees. So in our empirical study at Bayou, we found that polarization indeed can greatly improve the visibility under severe sun glare. Note the visibility of the small objects in the saturated area in the scene. As you can see, they are totally saturated in the unpolarized image, but clearly visible in the polarized image. As a result, because the polarization image brings back the information in the glare area, subsequent perception tasks such as stereo depth estimation can also be greatly improved. So again, now in the depth view, we zoom into this small object area. You can see that small objects in the clear area is not visible in the saturated image, but clearly visible in the polarized depth. Not sure if this is very visible in the slides, but this slide will be available offline. You can take a look at there for more details. Yeah, we can also visualize this depth better by looking at the point cloud. There's a video of the polarized stereo depth estimation. As you can see, the small objects over there in the saturated area is very clearly visible. Okay. Due to the time, I'm going to move on with the next slides. So in contrast, I have another visualization of a point cloud of state of our LiDAR. I guess one obvious thing you can notice here is even for the state of our 128 line LiDAR, the sampling is very sparse. So even though you might be able to capture the small objects with several couple field points within the scene, the coverage is probably too small for meaningful perception tasks like detection or segmentations. Yeah, so in addition, we can also, with the glare mitigation, we can also improve the semantic segmentation of the lane marks as well as the drivable area. As you can see, on the top here is a polarized view. You can see the lane marks very clearly, but because the high glares in the normal RGB image, the lane line will be very hard to observe, and subsequently the lines are missing in the segmentation result. By the way, this model we're using is a state-of-art lane line segmentation model called YOLO PV2. Okay, so. Okay, so the second visibility task I would like to talk about is haze and fog. As I believe one of the presenter mentioned before, the scattering of the light of air molecules produce linearly polarized light in a plane perpendicular to the incident light. Depending on the particle size, the scattering process can be formulated as Mie scattering or relay scattering. The polarization effect is most pronounced when the light scattering is caused by independent air molecule and very small, tiny dust particles in the relay scattering regime. So here, the air light becomes entirely polarized when the light source is at the right angle to the viewing direction, which is perpendicular to the incident. Otherwise, scatter light is partially polarized. So polarization-based dehaze method were proposed to perform dehazing for those partial polarized cases. Such as the classic work by Yoav Schechner. In this method, particularly, you will need two measurements of the worst and the best state of the polarized scattering of the polarized measurement of the scene. And then scattered air light component can be estimated and then subtract from the scattered image to obtain the clear image. And yeah, so in one of the work by this is actually Srinivasa's thesis. He has a very good summary of when you should use polarization for dehazing, whereas in other tasks you might want to go to other approach such as dichromatic based method for dehazing when you're when the scattering within the scene is not producing a good amount of polarization. So yeah, so this is, I guess we are a little bit over running out of time, so I will just be quick here. So for without using the polarization, you will also be able to use color information of the air light and object light to perform decomposition of the over the RGB channels of each given pixels. Yeah, so so we try to apply the instant dehazing work I just mentioned to our self-driving scene. To the scene we captured on the with the polarization camera mounted on our vehicle. And when there's when the particle size is too large, in that case, which will be it will be fog instead of a haze. When in those fog cases, directly applying the hazing method, I just described there, is not working very well. That's because the worst state image and the best state image don't have enough difference because the contrast of the polarization is poor. So in those cases, the hazel result is not so pronounced. But we are working on something that borrows the idea of a dichromatic dehazing on the polarization channel. And we are able to devise this method to defog those image instead of dehazing it. The results looks pretty reasonable. And on top of it, defogging, we can also utilize the DLP information to further assist improving the visibility by marking out the road area, because the road usually have high DOLP. As Achuda mentioned, I'm also going to show some example on rain and reflections in our perception task. So in some scenarios, if the incident angle and the index of refraction of the transmission media, air, for example, and the refracted material, water or glass, for example, are known, then it is possible to easily decompose the reflected component and the refractive component with polarization. There are many works on this topic. Here I'm showing one of the work, one of those works by and this is by Yan et al., which published in 2016 due to its simplicity and effectiveness. So here are some results of using that method in our real-world driving scenario. As you can see, if we are able to supply the index of refraction of the refractive material, in this case water, as well as specify the observation angle, then we will be able to kind of remove the reflection really nicely. For glass reflection removal cases with varying observation angles, deep learning based method gives very good results. In one of the recent methods, polarization reflection removal with one of the recent methods called like polarized reflection removal with the perfect alignment in a while. The author proposed a very clever method of capturing ground truth data for the training, where they unlike previous work where they find some removable glass and place in the scene and then take the image with and without the glass, they simply find the glass in the scene and then place some object, black curtain behind the glass to get the reflection only image. And then with the curtain removed, then you will get the mixed image. In that way, they create a much robust and larger data set for glass reflection removal. So applying that method to some of our perception tasks, images captured in the real world, we are able to decompose the reflected component and non-transmission component to some degree. And then it has some impact on the following perception tasks, such as monocular depth estimation. So without the polarized reflection removal, the modal depth estimator sometimes is confused by the reflection of for example, the person's leg here, right? If we want to get the depth behind the glass. But with the polarized reflection removal, the depth of the transmitted object can now be more correctly estimated given the reflection removed image. Yeah, so we can also, by supplying the reflection component to the monocular depth estimation network, we are also able to get the depth to the of the reflected component. And another relevant topic on glass is you will also be able to do semantic segmentation of glass area. And here I shows some results from Xiuwan's previous work as well. So in this case, this animation basically shows the original image in RGB. And we can see with the I kind of shuffled through RGB only glass segmentation and RGBP glass segmentation. As you can see, for the RGBP piece here stands for the polarization channel. If we introduce an additional polarization channel, the glass segmentation of the scene will be much cleaner. Okay, so the last item I would like to talk about in the visibility category is using polarization to improve scene contrast or help capture higher dynamic range scene. So in the case where when you have a black car, dark car in a dark asphalt background, the DLP image will really make the black car pop out because they tend to have high DLP values. This is because for darker objects, they are dominated by single reflection here, as you can see, which is highly polarized, where brighter objects tend to be dominated by multiple reflection, which is usually much less polarized. So as a result, for a darker in the DLP view, the darker car will actually look brighter, will have a higher DLP value. So that will help you to sometimes capture some car in some dark scenarios like this. In this case, underneath the overpass, there are actually several vehicles, which is completely invisible in a normal unpolarized view. But visualizing it with the DLP, you will be able to see there's several cars underneath there, which could be very this kind of early detection of object will be very it's essential to the downstream autonomy stack. And one other thing I would mention here is denoising needs to be, as Truda mentioned in his talk as well. The DLP or ALP representation sometimes is very noisy. So denoising step, pre-processing step is needed before we perform this DLP-based detection. And also another relevant topic is high dynamic range, right? As we can see that definitely in the glare removal scene, the intensity of the glare area or the light sources, polarized light sources, are greatly reduced. In that sense, you will be able to increase the dynamic range of your sensor, essentially. So how much dynamic range can we gain with the polarized sensor versus a normal RGB sensor, right? So in this work, back in 2000, which I believe 2020, so the author kind of formulated out the calculation of the delta change in dynamic range based on it's a function depending on the DLP. So essentially, with the high DLP value of the point A there shown in that table, you will be, which by the way is very common in the real world road surface. You will be able to get up to 16.4 dBs of dynamic range improvement. Okay, so for polarization-based semantic extraction, let's take a look at material segmentation first. The first speaker, Xiuwan, already covered a lot of the detail on the technical side of material and polarization. So I'm going to jump into the result here. So one of the recent work on this topic is called multimodal material segmentation by a group of researchers at the University of Kyoto. They built a data collection rig like this, which has cameras of different modalities, which includes the polarization. So in their work, they were able to collect about 5,000 images of the real world scene with RGB, near infrared, and employ AOLP and DOLP, as well as asking, they also asked workers to label the image with material labels. And as a result, they were able to train a network to perform material segmentation on the input image of given different modalities, RGB or NIR, or combination of different modalities. And several interesting results they were showing is by adding the polarization, it really shows big improvements in the segmentation results for metal, glass, and plastic. Those are kind of materials that you will see a dramatic difference in the polarization domain. And also, overall, by adding the extra modality of a polarization, it definitely helps with the performance of overall material segmentation. As you can see here, I highlighted the result of RGB only versus RGB plus 2 polarization channels. And one recent work in 2020 is this work where a group of researchers in France, they were trying to see whether using polarization will help you to perform vehicle and person detection better in severe weather. So the experiment setup they have is they try to they want to explore which kind of representation of a polarization. As we have gone through this talk, we've seen a lot of different representation of polarization, like AOLP, DOLP, given the 2 most mentioned ones, but there are also other representation of polarization, such as a Stoke factor, right? So they're trying to see what type of polarization representation will help most in the severe weather scenario. So what they have done is they have some pre-trained networks that can perform vehicle and person detection, and then they have a data set with both a good weather condition and a severe weather condition of the same scene. So they perform they have a pre-trained model. They perform fine-tune on the fine weather on different representation of the polarization, and then they perform fine-tune on that, fine-tune training on that, and then did the testing on the bad weather polarization representation. What they have found that was particularly there are some polarization that works, some polarization representation that works better than the other. One interesting finding is if you just give the raw polarization captures, meaning like a 0, 45, 90-degree polarization image, it actually performed the best compared to other ones such as like Stoke factor based representation, or HSD, which is I believe a combination of Stoke factor and then AOLP plus DOLP. But overall, they've shown that using the polarization representation, additional polarization channels, actually, I should not say like additional polarization channel, because you are essentially using polarization, 3-channel polarization representation versus RGB. You see that with 3-channel polarization information, you will be able to do better in this detection task in the severe weather. So last 2 results I would like to show are on the polarization shape estimation, which falls into the category of a geometry. So given that Truda already went through all this SFP work, I would just showcase several of our results using one of the method, the SFP in the wild from the Vladim's group. As you can see, those are the two results I've shown here already good results out of the whole set. But as you can see here, they still make some mistakes. For example, it seems to be hard for the network to figure out when there's a shadow or highlight present there. And this kind of surface normal map maybe look good when you're visually examining it, but if you're trying to get the depth map from this kind of surface normal map using integration, then the final reconstructed depth might not be of a good enough quality for that depth estimation, which is usually the modality that you will use in the perception in the planning task. So looking into the future, one thing we're actively working on is building up a large data set for polarization-based depth estimation. So like I said, why do we, so on one hand, depth is directly usable by the downstream autonomy agents, autonomy algorithms. On the other hand, surface normal are more related to polarization signal. In some cases, for example, the polarization, the angle of polarization will be just the projection of the 3D surface normal vector onto the 2D onto the 2D camera plane. Right. So in that case, it may not be something directly consumed by the downstream task, but it will be having a surface normal as an intermediate result there, as a constraint there, might be able to let you get estimate the depths more efficiently. And secondly, a lot of the SFP work we've seen so far are molecular depth based, right? However, like any other molecular depth network, it cannot provide metric accuracy, and it's a lot of the time very sensitive to the camera parameters. If you train on some certain camera, then molecular depth method may not work that well if you swap the camera in the testing time. On the other hand side, stereo depth can, on one hand, provides more accurate depth. And then, on the other hand side, it's also pretty robust to camera variation because at the end of the day, stereo is just doing the matching along that epipolar line. Right. So, and previous work in stereo or optical flow estimation network has shown that large random synthetic data set is a key to achieve SOTA state-of-the-art results for, say, stereo or optical flow estimation tasks. Example giving the very popular data set for Flying Things 3D and recent work in stereo depth estimation such as CRE stereo. Yeah, and as many other previous presenters mentioned as well, overall shape-form polarization might be a very difficult problem to tackle if you're trying to use a model-based approach because there are so many complexity there. For example, diffuse and direct reflection will have a different polarization model. There are also, as Jingwei mentioned, zenith angle ambiguity, right? And then there are also different material will have a different index of refraction, which also adds on another layer of complexity there. So it's natural to solve the shape from polarization or depth from polarization using a data-driven approach. So what are the existing data set there? We feel like the existing data set is shown here. are mostly have three problems, as I pointed out here. So one is the data set size. Even the largest data set, real world data set, which I believe is the SFP in the wild paper, they only have a couple thousands image, so which is far less than the sufficient number of images that you would need to train a reasonable network for example, stereo depth estimation tasks. To just give you some ideas, the state of our CRE stereo data set has more than 200,000 images. And then with such a larger data set size, you will get very robust and stable depth estimation in a while. And the scene complexity of a lot of the data set were very basic. Usually it consists of very dedicated lab setup of some certain simple materials with very controlled lightings. The SFP in the wild paper does have real world setup with natural objects and materials, but the problem is the ground truth they use to train such a network is the quality of the ground truth is not very high, because they use a Kinect, which is a time of flight camera, which works in indoor. So all the scenes they captures are indoor. So we don't actually have a large scale outdoor data set for the problem of the stereo polarization depth estimation or shapeform polarization. So as such, we are building a larger data set, a large scale data set of a polarization signal in the style similar to Flying Scenes 3D, where you basically just have a lot of random objects to cover enough random cases, corner cases, normal cases of the polarization and the stereo. And here is a video of changing lighting, the impact of the effect of the changing lighting to polarization view. And this kind of a data set will be very helpful in solving the lighting invariant shapeform polarization and estimation problems. Yeah, and at the same time, given that we have a large data set to train the model, we also would like to have a real world data set to fine tune the model and validate the model with the real world scene. So we're also building up the setup where you have a polarization, stereo depth, as well as a LiDAR across different modality. Okay, so with that, that's the conclusion of my talk. I went through some of the ideal applications to use polarization in real world perception tasks. Hopefully that will inspire you to try out polarization in your specific task. And looking into the future, besides the depth data set problem I was talking about, I think there are also some problems worth examining in the low level polarization domain, such as denoising and polarization demosaicing, because right now with the newer type of polarization sensor, you will have a very, very large color filter, polarization filter kernel, which is now like 4x4, whereas your normal RGB filter kernel is only 2x2. Here's a reference of paper cited in this talk. And with that, I would like to thank you everyone for listening to my talk. Like I said, we are a company in the Bay Area, and we are closing our Series A round, and we are actively hiring experts in simulation and GPU acceleration. And yeah, I would like to thank all the colleagues without whom this the work I present here is not possible. Thank you, everyone.
We are already 6 minutes over time. If you guys want, maybe just one question for George.
Or we actually have a, like a lunch gathering, I mean, offered by Vayu. You guys feel free to join us and we can chat more, there. And that's everything we have for this tutorial. Thank everyone for attending.
Thank you.
All right.